Okay, this is your Chapter 10 recording, and this chapter is Fluid and Electrolytes and Acid Base. Your podcast is not completely the whole chapter. It's just part of the chapter. Some of the other things that are in the chapter we're going to actually do as a lab activity. So what I'd like to start with for fluid and electrolytes, and we're starting on page 186, it is important to know what homeostasis is. A lot of these components to this chapter kind of take you back to A and P. So with homeostasis, we know that it means it's the ability to maintain internal equilibrium by adjusting to physiological processes. That's important for our body to maintain homeostasis. If we do not, and something causes awry, then that throws off the balance in our body. And as you can see, and when we talk about this chapter as we go through, think about patients who have diabetes. They end up in kidney failure if they're non-compliant over the years, and then they can have heart disease or heart failure. All of those disease processes take you back to fluid and electrolyte balances and acid base. So when we talk about fluid and electrolytes, we must remain consistent. We have fluid volume, we have electrolyte composition, and then we have the pH of the intracellular fluid and the extracellular fluid. Illness and trauma can cause a change in that balance, and fluid and electrolyte balance in the body involves regulatory mechanisms that maintain composition, distribution, and movement of fluid and electrolytes. So the slide that you're looking at now is your body fluid composition. So when we're talking about body fluid composition, we talk about water. And when we think of water, it is the primary component of the body. It is the medium for transport and exchange of nutrients and other substances such as oxygen, CO2, and metabolic water from the cells. It assists in regulating body temperature through evaporation and perspiration. The average fluid intake and output is about 2,500 milliliters over a 24-hour period. So just keep in mind that was 2,500 milliliters over 24 hours. Also, when we think of urine per day, that is required to excrete metabolic waste, because we know it is important for our body to get rid of that waste. If we do not get rid of that waste in our body, we have this toxic buildup, and that is not good. So in order to excrete the waste, it's 300 to 400 milliliters a day. There is a breakdown of the intake and output table. It is on page 187. I'm just trying to flip through. There we go. 187, excuse me, and it's your table 10-1. It's looking at a 24-hour period of fluid gain and loss in an adult, and it just kind of gives you a breakdown of where you're losing that fluid. You can see that the bulk of the fluid is water and food that is taken in, and the loss is the bulk is from urine. Now we're going to talk about the electrolyte component. And for electrolytes, it's substances that dissociate in solution to form charged particles called ions. You have your cations, which are the positive charge, and you have your anions, which are your negative charge. And I'm just going to write those down here in the corner. And you can always think of anions when you think of A usually stands without, so think that's always a negative, and then your cations are the positive. It assists with regulation of that water balance. It regulates and maintains acid base. and it's essential for neuromuscular activity. If there is an electrolyte imbalance, there can be serious neurological activity deficits that occur. Okay, we're going to talk about body fluid distribution. That is in regards to intracellular fluid, which is within the cells, and extracellular fluid, which is outside the cells. I do want to just let you know that on page 188, table 10-2, the normal values for electrolytes in serum osmolality, do not pay attention to that chart. I'm going to give you in class, or I think I actually posted it on Blackboard, there is an NCLEX Need to Know lab sheet. Those are the values that you will go by for the rest of the nursing program. They are based on NCLEX, so instead of getting confused, we use those throughout the courses. You will notice that when you go to clinical and Winchester Medical Center, sometimes their normal values will vary a little bit. But for you all, because you do have to take NCLEX, we go by the NCLEX Need to Know lab sheet, which is what I posted for you. So when we're talking intracellular fluid, that is within the cell, and we are talking about potassium, we are talking about magnesium, we are talking about phosphorus, we are talking about glucose, and oxygen. Now, when we're talking about extracellular fluid, we are talking about sodium, chloride, and bicarb. The other things that your chapter talks about is interstitial fluid. Forgive me, I made a blank slide, so you're going to see me writing. This is in the space between most of the cells in the body. Then you have your intravascular, which you see me spell wrong. Intravascular is the plasma in the arteries, the veins, and the capillaries. And then you have transcellular. Transcellular fluid is your urine, your digestive secretions, perspiration, your spinal fluid, and then it is also your pleural, synovial, intraocular, gonadal, and pericardial fluids. You also have to keep in mind that the cell membrane is permeable. What this means is that it's allowing passage of water, oxygen, CO2, and small water-soluble molecules. You do have capillary membranes that separate plasma from that interstitial fluid, and then plasma from the interstitial space. You have epithelial membranes that separate the transcellular fluid from the interstitial fluid and plasma. So you want to know, why is all that important when I'm talking about intravascular versus transcellular versus interstitial? When you have a patient who does not have functioning kidneys, their fluid can't be filtered. So when you can't filter the fluid has to go somewhere. That fluid ends up backing up into the body and into that interstitial space, and then you have something that is called third spacing. So everything plays a vital key in where the fluid is, where the fluid can move to and back, and then we're going to move into talking about osmosis and diffusion. And if you have a patient who is third spacing, what types of solution, rather IV solution, can be given to help correct some of those imbalances. Okay, so now we're going to talk about body fluid movement. And when you think of body fluid movement, you can't help but discuss osmosis and diffusion. So osmosis is where the water moves across a selective permeable membrane, and I'm just going to put perm and MEM for membrane, from an area of low solute to a concentration of high. So again, osmosis, water's moving across a selectively permeable membrane from an area of lower concentration to an area of higher concentration. So when we think of osmosis, we're going to talk about colloids, isotonic, hypertonic, hypotonic solutions. These are solutions that can be given to help correct some of those imbalances. So a colloid is the solution, the power of the solution to draw water across a membrane. It's osmotic pressure of the solution. So this is where you would have a patient who is third spacing, and you need to draw some of that fluid back into the cells. So an example of a colloid would be a medicine called albumin. Don't get too hung up on this. We're going to talk more about colloids, isotonic, hypertonic, and hypotonic as part of your lab activity for this week. The other thing is as I said, if you have a patient who is third spacing, you're trying to pull that fluid back into the cells. So it's pulling from that interstitial space into that intravascular compartment. That's the colloid. Now when we talk about isotonic, it's the same concentration as plasma. So here's your isotonic. It won't shrink or swell. There's no net gain or loss of water, and there's no change in actual cell volume. An example of isotonic is your normal saline, but it's the 9% normal saline. When we think about a hypertonic solution, and I'm going to erase what I have written so we can have some space to talk about hypertonic and hypotonic. So when you have a hypertonic solution, this is the greater concentration of solutes than plasma. So the water is drawn out of the cell, causing that cell to shrink up. It isn't your normal saline, but it is 3% normal saline. Hypotonic solution is a low solute concentration than plasma. So they're opposites, hypertonic. And this is the case when the red blood cell is placed into a hypotonic solution. That water moves into the cell, causing that cell to swell and rupture or hemolysis. So your hypotonic example would be your 0.5% normal saline. All right, so out of all of that, osmosis and these different types of solutions, So why is that important? When you have an increased sodium in that extracellular fluid, this is pulling water from the intercellular fluid, causing the cells to shrink. So if I would give a hypotonic solution, I'm going to reduce sodium concentration and osmolality and try to move that water back into the cells. I'm trying to take the fluid and use it to help go back to that homeostasis state. Okay, I added a blank slide so we can talk about diffusion. So diffusion is the solute molecule moves from an area of high concentration to an area of low concentration. There is simple diffusion, which is a random movement of particles through a solution. There is facilitated diffusion, which allows large water-soluble molecules to diffuse across a cell membrane. And then and these are just definitions of diffusion. This is just to kind of remind you of what you probably already had learned in A&P. Now we're going to talk about filtration because remember, osmosis, diffusion, filtration, active transport, fluid regulation, those are all important key components into maintaining fluid and electrolyte balance. So with filtration, we are talking about the movement of water between intravascular and interstitial space in those capillary beds of the body. Then when we talk about active transport, we think of molecules moving across a cell membrane and the epithelial membrane against a concentration gradient. So it's moving the cells and the epithelial membrane against concentration. Then this also, in order to have active transport, it requires ATP. So it requires energy from ATP and a carrying mechanism to maintain that higher concentration. So we have to have some energy to maintain that higher concentration of a substance on one side of the membrane than the other. So we need more force on one side than the other or we can't maintain that balance. So an example of active transport is the sodium potassium pump. They have to work together to maintain a balance.